In this video, we will be covering exponents and the terms accuracy and precision. Okay, so in chemistry, you will encounter very large or very small numbers. For instance, right here is a very large number. This is the number of carbon atoms that would be in about 12 grams of carbon, or a 60-carat diamond ring. Now that is quite a large diamond, but on an everyday scale, it's not such a large object, but it has many, many atoms in it. On the other hand, if we wanted to look at the size of one atom, that would be a very small number, right? So here is the size of a gold atom in meters, right? It's a very small number. So the size of an atom is so small, we really cannot see the outside of an atom. Gold is a large element, but this is as close as we can get using an electron microscope. So how do scientists simplify very large or very small values that contain many digits? Because we certainly do not want to write all those zeros. So we use scientific notation. So a number written in scientific notation will have a coefficient, which is the number in the front, and that should be between 1 and 9, right? Times 10 to the, and that's your exponent. And it can be a positive value if you have a very large number, or a negative value if you have a very small number. So let's go back to those numbers we had at the beginning. Okay, so if I wanted to write this number in scientific notation, right, here's where you would start your decimal. Okay, and you would just count going to the left, 1, 2, 3, 4, 5, 6, etc., all the way until you get that decimal right after the number 6. Because remember, in the coefficient, we want that number to be between 1 and 9. So that turns out to be 6.022 times 10 to the 23rd atoms. Okay. So even though that number is equivalent to, say, 60.22 times 10 to the 22nd, remember, by convention, we do not want to have 60 as a coefficient. So we would move that decimal and get it back to 6.022 times 10 to the 23rd. Okay, so you do need to write your numbers in scientific notation with the coefficient being between 1 and 9. Okay, let's look at this small number. Okay, so again, right here, you would start with your decimal over here, and you'll count going to the right now, 1, 2, 3, 4, right, all the way, okay, until you get 1.66 times 10 to the negative 10 meters. Okay, so again, make sure that decimal is right after the 1. All right, so let's do a little bit of practice. Okay, so here we have the diameter of the Earth. And let's get that into scientific notation. So we will start with our decimal right here. So we're moving it 1, 2, 3, 4, 5, 6, 7. So 1.28 times 10 to the 7th. And that is in meters. Okay. And the length of a virus, this is a very small number, so we'll be moving the decimal the other direction. That's 1, 2, 3, 4, 5. So 3 times 10 now to the negative 5, because that is a very small number. And the mass of a human in kilograms, excuse me, although we would normally leave it at 68 kilograms, but if we had to put that in scientific notation, it would be 6.8 times 10 to the first power, and that's in kilograms. And I almost forgot my units on the length of the virus. Okay, very good. Now, it is important that you know how to use your scientific calculator, because you will be experiencing large and small numbers in chemistry, and you need to be able to input them into your calculator. Okay, so I asked you to make sure you bought a calculator with an exponent key. And you can see it down there, right here in red, right? That's what it looks like on this calculator, EXP. Others, if you use Texas Instruments, it's usually listed as EE, right? And other calculators might use 10 to the X. Okay. All right, so if we were to calculate in number 1, right, using this calculator, what it would look like when I'm plugging it in, it would look like 6E is what will show up on your calculator screen, right? 6E to the third power, right, times 5E. Now this is a -5, so you want to be sure that you use this negative button right here. Okay, so you're not using the function key over here. This is just labeling that as a negative. And that's a -5. Oops. Okay. That's what it would look like, and your answer would come out to be 0.3. Okay, next problem number 2. Plugging this into your calculator, you would need to use parentheses because we're taking this exponent to a power of 4. So we would do 7e to the third, close parentheses. Then we're going to use this up caret button to the 4. Okay, so that's what it should look like when you plug it into this calculator. And the answer you should be getting for this one is 2.401 times 10 to the 15th. Okay, so please do try these on your calculator and make sure that you are getting these answers. Okay, next one, 6 times 10 to the third. It would look like 6e to the third. And this time we're adding that. So just plus 1 exponent to the 4. And this answer would come out as 16,000. Okay, so very important that you know how to use your calculator. All right, moving on to accuracy and precision. Okay, these are terms that we use when we're talking about measurements from the laboratory. Okay, so how do scientists express accuracy or precision, excuse me, of a measurement? Okay, so the term accuracy means how close your measured number is to the actual, right, expected or true value. So for instance, if we had a 100-gram standard and you put it on a balance right here, and you see that it weighs 100 grams, right? That is accurate. We're expecting it to be 100 grams because it is a known standard. And this one over here, right, is inaccurate because it is not reading, right, 100 grams. Okay, so this measurement is accurate. This one is inaccurate. The precision, right, of a measurement is the extent of the agreement between repeated measurements of its value. So normally in the lab, you will repeat your measurements, right, to make sure that you have the right reading. And so here's an example of a measurement that was done 3 times. And the mass was recorded, right, here 1, 2, and 3. And we can see that they're all very close together. They're all very close to each other. So we would say that this measurement, right, these measurements are precise. Okay, so this is often used as an analogy. This is a target. And if 100 is the actual value, right, that we're expecting, and the dots, right, those are like the darts that were thrown. They are the independent measurements, right, the repeated experiment. And so on this first example, we see that all the experiments are close together, that it is reproducible, and they're also very close to the actual value. So we can say in the first target that this is accurate and precise. And in the second target, we see that all the trials, right, are close together, that it is reproducible. But they're not hitting the mark, right? They're not giving us the true value. So in this instance, we have precision, right, but not accuracy. Right? It's precise but not accurate. And in this last example, we see that our experimental trials are kind of all over the place. They're not similar at all. It doesn't seem to be reproducible. And we're not getting the true value. So this is not accurate and it's not precise. Okay, let's look at an actual experiment. And this is just showing experiments done by 1, 2, 3, 4 students. And each student carried out 3 trials. And this was to determine the density of gold. Right? And it is known that the density of gold is 19.32 grams per cubic centimeter. And if you have pure gold, that's what the density would be. That's what it should be calculated in the lab to come out to, right? That is your actual density. So let's take a look at student number 1. And we see for student number 1, we have these 3 measurements, that they're all very close to each other. The average of those 3 measurements is exactly, right, what is expected for the density of gold. And so we would say this is accurate and precise. You're looking at student number 2. Here's your 1, 2, 3 measurements. And they're not close together. Here's a low measurement, here's a high measurement. The average is not close to the true value. And so we're not seeing accuracy or precision in this example. Okay, let's take a look at student number 3. Here are 1, 2, 3 measurements. And we can see that they're all very close to each other. And they're very close to their average, each of them. So we are seeing precision, but the final averaged answer is not close to the actual density of gold. Okay, so this is precise, but not accurate. And in student number 4, we see a very low measurement, high measurement, slightly high, but averaged together, interestingly, you can get an answer that is close to the true value, even though your measurements were not very good. So sometimes this happens and you will see that it will appear accurate, although you just got lucky because it is not precise.